So we're trying to look at the relationship between the volume of a sphere and how we can be able to use a pyramid in order to represent the specific, or how we can be able to derive the volume of a sphere using a pyramid, the concept of a pyramid. And we have said that suppose there's a pyramid that is put into this sphere, whereby the base of the pyramid forms the surface and then the apex of the pyramid is located at the center of the sphere, then we can have a relationship in that the radius of this particular sphere is represented using the height of this pyramid. Therefore, we have said that all the bases of the pyramids will represent the total surface area of the sphere, which is given as 4 pi r squared. Therefore, trying to find the total volume for this particular kind of a sphere is the total number of pyramids that you have represented as n times the volume of an individual pyramid. So in this case, this is going to give us a clue on how we can be able to solve that. So as we have said, there's a relationship between the volume. That one I'm just going to mention it so that we can be able to use it somewhere. So there's a relationship between the volume and the surface area of a sphere, in a sense that the volume is represented, or the surface area is represented as 4 pi r squared, and the volume is given as 4 pi r cubed. So this is over 3. So this is going to give us 3 over r as the ratio between the surface area and volume of a pyramid. So this particular relationship is the one that we are going to exploit in trying to find or figure out how we can be able to represent formula of course, the volume of a sphere. So if you try to look at the relationship on the board, so I've said the surface area over the volume is equals 3 over radius. Now we have said that the surface area can be given as 4 pi r squared over the volume is equals 3 over r. So making V the subject of the formula for volume, we will have V is equals 4 pi r squared times r all over 3, which is 4 pi r cubed over 3. Of course, which is going to give us the volume of a sphere. Now, of essence, is this relationship that exists between the surface area and the volume of the pyramid, which of course we have given the volume of the sphere, which we have given above. So in trying to look at this relationship using from the concept of a pyramid that we have of course stated, therefore we are going to see that there's a general relationship which I'm going to illustrate, which is of course, as we said, volume of the pyramid is equals a third pH, where H implies R, therefore V is equals a third PR. And when we are trying to look at the concept of this surface area, which is equivalent to base of a single pyramid times n pyramids, which will give the total surface area of a sphere as that. Now this one, of course, we can either use the relationship between this one and this one in order to find, of course, one of the missing variables or concept. And basically, the base area that we are saying in that still we can, given one of them, we can be able to find another one. So that is the relationship that exists between the two and the way in which we can be able to derive the volume of a sphere using pyramids. So I've basically tried to limit the relationship between this 3 over r and the surface area and the volume, so that we can be able to discuss on our next move. But when we are going to have a sample question, I'm going to illustrate on how that one can be basically achieved. So in that case, I'm also going to look at that. So having looked at the representation of a sphere And having talked about the surface area and how we can be able to represent volume, I'm going to look at the third and last, perhaps the second last concept that is going to assist us as well. And that is the equation of a circle that is derived from the concept of Pythagoras theorem. So we have a circle of that nature in the y-x. Those are the y-x direction. That's a two-dimensional surface or plane. So we have that particular representation for a circle of radius r. So this is the origin of radius r, and this is the distance for x and y respectively. So there's a formation of a triangle in the middle or inside that circle that is prescribed inside that circle that I've written using for the base height and the hypotenuse. So using Pythagoras theorem, we said that r squared can be given as y squared, or no, okay, y squared minus x, or y squared plus x squared. The hypotenuse squared is equals the sides, the product of the squares of the sides. Therefore, we can give y squared as r squared minus x squared. So that is the equation for two-dimensional space for that particular circle. Of course, we can just simplify it and say y is equals the root of r squared minus x squared to represent a function which is going to give of course, that particular set of or just that curve which is represented as a circle. So in this case, we're going to consider this formula and trying to find how we can derive a formula, or how we can be able to derive a formula for volume of a sphere given a particular curve. So in this case, we're going to consider two specific points still on the x and y plane, and from there, so this is going to use the concept of the disk formula, and we're going to use this particular setup in order for us to try and interpret. So suppose there's a curve that runs from negative r from the origin to positive r on the xy plane, then we can be able to represent that using, of course, the expression for just that function to represent the curve x squared. So from the Pythagoras theorem, I've demonstrated how we can be able to achieve that. And if we rotate it about the x-axis, if we rotate this curve about the x-axis, the sphere of radius r will be formed. And maybe I can be able to take this one out so that we demonstrate. So I've said that this curve is represented by the root of r squared minus x squared. And therefore, if we try to do a rotation along the x-axis of this particular curve, and this will form a volume of radius r, or maybe a sphere of radius r. And this, of course, still we can be able to represent it using this kind of the circle that we have been already expressing about. So in this case, the volume can be found using the concept that we call the disk formula. And this disk formula exploits, or maybe is founded on the concept that this sphere is made up of concentric disks, which I can just represent one of them like this. Now from this point, it's made up of various kinds of disks, whereby an individual disk has got an area A. Now that I've demonstrated from part 1 of our explanation the concept of an area of a circle, we looked at the concept of an area of a circle, especially for a sphere, the area of a circle, a great circle. And we said this area can be given as pi r squared. So the volume, therefore, for this kind of a disk can be given as pi r squared h. So in this case, if we're having a curve that is represented as such, we can do an integration in order to find the volume using this disk formula, which of course states that volume of such a kind of a function. Now, for this function, still can be represented as y squared, finding the square of that, r squared minus x squared. For a two-dimensional space, this is how we can be able to represent. Now, the volume, the disk formula states that the volume of such a kind of a sphere that will be formed from the rotation of this particular curve will be represented as an integral of, this is pi, the product of pi and the integral from of y squared with respect to x. So that is y squared dx. So this basically is what we call the disk formula. And we're going to see that this also is going to lead us to the general formula that we have described for finding the volume of a sphere. So just to do away with this. So as I've said, this is the disk formula. But you can use the concept of integral calculus to try and find out how it can be represented. So therefore, we're going to say v equals pi integral from r negative to r y squared dx. Substituting for y squared, now that we have said y squared is equals r squared minus x squared, we therefore say is the integral from negative r to r y squared, we do a substitution, r squared minus x squared dx. So this pi here. So therefore, this one we proceed can be written as we do an integration for this. So it will be r, of course it will be r squared. We are integrating with respect to x. So r squared x minus x cubed over 3. So this one we have just divided by 1 because of that exponential, but just give the same result. So for this one, we're going to divide by 3, and then we're going to find this from the range of negative r to r. So if we do a substitution for that, of course there's a pi outside there. So therefore we will have doing a substitution for that. So it is r for r first, r cubed minus, so we have substituted x for r, so this is r squared times r cubed minus, we do a substitution for this one, it will be r cubed over 3, and therefore this is for r. So we find the difference between a substitution for r, just to do a normal integration. So this is minus the second part of it, so we do a substitution for negative r. This is going to be minus r cubed. So this is going to be an addition because of a substitution for negative. Negative is going to be plus r cubed over 3. And then this is going to give us, just a minute. Of course, going to give us 4 over 3 pi r cubed, which is the volume of a sphere. So using these two approaches of using the pyramids and the relationship between the surface area and volume of a sphere, and basically the concept of the disk formula, we can be able to just play around with these specific concepts together and find out how we can derive the volume of a sphere. So that is it for today, guys. I hope that this is going to assist us somewhere. If we come across a problem of the kind, we can be able to solve it. So that is it for today. Bye. Thank you. God bless.